All right, can we see this okay? Do we need lights off? Pick. Lights on or lights off? Okay. And will you somebody pull that door shut, please, just so we can try to capture as much air conditioning as possible? I've been told the air conditioning is technically on in here, but it's definitely not on in the hallway. Yeah, I don't know if that's cold air return or that might be cold air return or what. No, those are usually low. I don't know. They just told me the air conditioning is on. My office is quite comfortable. Yeah, I'm in one of those places where they say keep the door shut so we don't let the steerage come in and get too much free air conditioning. So I have like 3 students camped out in my office right now doing homework. All right, so last time we were kind of going through and rehashing some stuff from our 200 class just to kind of bring us back up to speed. So we reminded ourselves how human beings solve problems. We started kind of making this list of what Java is and what Java isn't, because Java is going to be this language we're going to be using in here. So we decided Java was object-oriented. That was the telephone example over here where, it's a language that supports this idea of allowing us to organize our programs in such a way where the details that need to be written at least once can be hidden inside, encapsulated inside of objects, and then we only have to expose the actual parts of it that we're going to work with. So Java is a little bit more modern language that gives us those abilities. So the difference between an object-oriented language and a procedural language is just one level of, so we got little lights off, okay? So it's just one level of organization. Just like in real life, how we sometimes try to come up with little systems to make our lives easier. Okay, we're going to get the flicker. That's going to be annoying. It's a strongly typed language, so that means that we need to define the kinds of values we're going to store in our variables before at the time we define our variables. All right, it's a high-level language. Started talking about that last time as well. High-level language meaning it's kind of a power tool. So every line of code we write in Java translates into a whole bunch of magic tricks the CPU knows how to handle. All right, and then we kind of said it's a compiled-ish language. So mostly it's a compiled language, but technically it runs inside of a virtual machine, so it's interpreted a little bit. But in general, we can think of Java as being on the slower side of our faster languages, if that makes sense. Okay, nothing wrong with Java, and it's an excellent teaching language. I think I mentioned last time because I don't have to worry about what kinds of machines you have, and we'll talk about that a little bit more today when I introduce the actual tool we'll be using to do this. And your second homework assignment is already up. Basically, it's going to be a monkey see, monkey do thing. I'm going to be downloading Eclipse today and writing a Hello World program in there, and you'll be doing the same thing for Tuesday. And at that point, I'll know for a fact that everybody has their environment set up and can do homework. Make sense? So a couple of free assignments there. If you didn't do the first one, which was due today, which is the Slack, post your stuff, then I guess you're an idiot. So I guess take that for what it is. Anybody not do it, by the way, just to kind of call you out in class? That'd be really funny. All right. Perfect. Actually, I think I put him in there and everybody did do it, which was disappointing to me. I usually like making fun of somebody. Okay, so we started kind of going through how humans solve problems. All programming languages attempt to emulate these things. So every single one of our programming languages is going to have facilities for memory, asking questions, and repetition. What's the purpose of a programming language? Lets us tell this alien being that is a computer what to do. Human beings are really, really, really smart. We're really used to talking to other human beings and problem solving with these complex critters that are people. But as soon as we start dealing with computers, it's very difficult for us to slow our minds down to actually get to the point where we're talking to a computer. That's the difficulty in programming, not the language itself. Okay, so I'm a big advocate of all programming languages are the same. Once you have the programming skill set, learning a new language is no big deal. A couple of you in here are taking the 390 class this semester, which is the Apple Watch programming class. So in that class, we're learning a brand new language, and most of the people in that class are learning a brand new language because the language isn't very old. We're using a language in there called Swift, which is an Apple designed language that looks a whole lot like Java because they want to get those folks over to the dark side. But the punchline is if you've had programming before, learning Swift is not going to be a big deal. If you are in this class and really haven't had development before, learning Swift isn't a big deal because you're going to be learning programming anyways. So you're going to see there's a whole lot of similarities between what we're doing in there and what we're doing in here. Okay? Little tiny syntaxy type changes, but in terms of mental problem solving, it's all the same. All right, so then the mapping. So I guaranteed you last time that 100% of programming languages will have facilities for these three things. Variables, conditionals, and loops. If we can learn how to do those three things in any language, we're off to a great start in solving a whole big classification of problems in that language. All right, so we started talking about variables in general, kind of this first fulfillment right here, okay? And so these are name containers, so name value pairs, name containers for holding information, and we use it to emulate memory. So inside of our programs, whenever we need to remember something that we're going to use later on in the program, we're going to throw it in a variable that makes it available to us later, all right? If we're only going to use a value once and be done with it, why throw it in a variable, right? We'll use it, we're done with it. Those are called literals, okay? So let's go ahead and throw that in here. So a literal is a fixed value that we typically, well, let's say that we can store within a variable if we need to use it again. But we can also just use it directly. So first week of school, how many of you are starting to get sick yet, besides him?
I've been sick.
It's like a petri dish. Everybody comes back. I start a course of this stuff called emergency. You know what it is? It's like the I don't know, 15 million milligrams of vitamin C or something like that about 3 weeks before school starts, and I still always get sick the first semester. You guys are bringing back your diseases from your trips in northern Wisconsin. All right. So, in any case, that's what a literal is. So, examples of literals is like 5 or 7 or a, things like that. Okay. Technically, we could say hello is sort of kind of literal, but really that's a collection of literals. But same diff. It kind of fits my little definition here. And knowing exactly what a literal is isn't as important as knowing what it isn't. A literal is not a variable. Okay? So literals are things we can throw into variables, but if we don't need to reuse something in a little bit, we wouldn't use a variable. So that's the rule of thumb for when we use variables. Okay, and we'll look at syntax for variables in Java here in a few minutes. Okay, so we kind of started talking about, reviewing kind of our evolution of languages, and we're kind of sitting over here on these languages. So we see C to C++ to Java. Swift kind of fits down here somewhere. And these are all languages that ultimately get compiled and talk directly to the CPU, as opposed to the languages over here, which are just as important, just as good, little bit different kinds of language. These guys are going to be loosely typed. They're going to be interpreted. Those just become kind of the nature of the beast, I guess. So those change our mindset a little bit when we're programming with them, but we're still applying the exact same problem-solving programming mindset. That competence translates across the board. Okay. Over here, though, the output of our programs will be HTML and JavaScript. That is things that web browsers understand. Over here, the output of our programs are going to be things that the CPU understands. So we're going to start off in here with a lot of text-based stuff because we're really trying to drill the competence of programming. The second course, the CSC250 course, we get into data structure. So taking the foundation of the stuff we learn in here and starting to build new interesting widgets that have kind of a theoretical proof in helping us solve more complicated problems in more efficient ways or something along those lines. All right, so those two classes kind of go hand in hand, the 250 and the 300 course next semester. I'd encourage all of you to take both of those. If you're a computer science major, you have to. If you're an IT major, I encourage you to take the 300 course. I think you're doing yourself a disservice when you don't take it, not just from having that programming background, but also when we fast forward to the upper division classes, which typically assume you've had 300. But we have a bunch of IT people taking them who haven't had 300, so it becomes a little bit of a disadvantage for you. So, I guess not my problem, but whatever. Okay, so kind of looking at the two broad classifications of languages, we're focusing over on this side of things. We talked about the evolution of C, and C is kind of a variable-based evolution. So we look at C through the we look at that as kind of the father of all of our modern languages, and really we think about C as having its limitation set within the idea of variables. So we have the name-value pair, single name with a single value. That's our typical stock variable. We have this thing called an array, which is a single variable name that holds a collection of literals, collection of stuff. Okay? We have this thing called a struct in C. They don't exist in Java, but they existed in C. And a struct allows us to have a single variable name with a collection of name-value pairs. So we can have like a person is, name is Mike, age is so on and so forth. Okay, so we can do things like that. Okay, and C was a procedural language. So this is that guy that predated our object-oriented languages. So all the wires, as Jonathan pointed out last time. I'm very impressed that you retained all that stuff. Most students don't. Especially when you leave school in the spring and you come back in the fall, it's like a reboot. So
I worked at a place that kind of.
Oh, you kind of kept doing the stuff, so you never actually had an opportunity to forget it? Plus you're kind of in that weird age group here where, I mean, not that you weren't already, but a lot of birthdays, turning 21 type stuff, and a lot of alcohol. That's kind of what starts happening. What was it? Oh, we're talking about alcohol. That's right. All right, so this is C. C, great language for a very long time, still used today. It's not like it's been forgotten, but has some weaknesses, especially for us as modern programmers. But something I want you to think about as we go through this stuff, that with Java, we are very much using a modern, I'm going to say modern-ish programming language. It's not like Java's a week old. Java really came out like in 1995. So it's been around for a long time, but C's been around since like 1968. Okay, a lot longer. All right, so relatively speaking, Java is very new. Swift is only 2 years old. It's the young pup. All right, but we'll see that they didn't really make that many changes, evolutionarily speaking, from Java. So we can say that Java is a pretty good language in terms of using it as our programming basis. All right, so then the evolution of C++, why did we need this is kind of the punchline. We started seeing as our computers got more and more powerful and we started using them to solve more complex problems, we started seeing weaknesses in C. So that C programming language didn't quite allow us as computer programmers to do everything we wanted to do in as convenient a way. So we didn't know we needed certain constructs in C because we weren't using those constructs early on. Computers got faster, human beings got lazier, we decided we're going to start using computers to do even more crap. All of a sudden we needed a little bit more evolved language for doing some of that crap. Okay? And at the end of the day, the difference between our procedural language C and our object-oriented language C++ is this dude right here, this introduction to this thing called a class. All a class is a struct that allows us to stuff methods inside of it. Okay? That's it. No difference. All right, we looked at a little bit of an example here last time where we started to look at it looks like. So with a structs kind of look like this, but we might want to have a function here that goes and displays everything about a person. Okay, maybe displays everything about a person. And so if we were writing that function, well, first, let's give a definition of a function here, just to kind of fill this out. So they were still called functions in procedural languages like C. In C++, when we transitioned to object-oriented languages, functions got renamed to something called a method. Okay? In C, we had things called functions and procedures. So in general, we're going to say a function is a reusable chunk of code that we write once and can call multiple times, passing in various inputs. All right, real life example, all of us know how to add. So if I say add 2 and 3, you're going to say 5. If 2 seconds later I say add 5 and 4, you're going to say 9. You use that exact same adding method, that exact same adding facility in your brain, but you took in different inputs, applied the addition function to it, and got a different answer. Make sense? So that's what functions are. We write them once, and we reuse them with different inputs, hopefully getting different answers. All right, makes our life a little bit easier. Historically, in languages like C, a function was something that returned a value. A procedure was something that did not return a value. All right, so an example of that might be if I say pick up the pencil. Well, I'm asking you to perform an action. So you bend over, you pick up the pencil, you stand up, but you're not actually giving me anything back. You just picked up the pencil. Okay, so you're doing something, you're performing some actions that you can do over and over and over again, but there's nothing that you're returning to me. I'm not asking you to hand me the pencil. I'm not asking you to say you're done. Just pick up the pencil. Okay, that's a procedure. Function would be same thing, but hand me the pencil, or the whole, what's 3 plus 5, spit back 8, that kind of stuff. Okay. With our modern languages, when we went to object-oriented languages, functions and procedures got squeezed together into a single monster called a method. They're the same thing, just different names for the same crap. Okay? So methods always have a return type, but sometimes that return type is void, meaning nothing will be returned, making it essentially a procedure. Okay? So this is just kind of connecting Java to our older languages. All right, so back to this guy and talking about functions. We may have wanted to have a function in C. Maybe we would have had something called a display person, and this guy would have taken a person as a parameter. And don't worry about the syntax here too much. We're just going to get used to looking at some of this stuff. And inside here, we might want to say, if we're doing this in C, we would say println %s something along those lines. %s and %d are placeholders, so this is a placeholder for a string. Actually, I probably should say my name is. So this is a placeholder for a string. This is a placeholder for a decimal value or an integer. So this will say my name is whatever P's name is, and I am whatever P's age is, years old. That's what it'll print out. Okay? Don't worry about that too much right now. We'll practice that crap a lot. What we're really talking about here is what are the weaknesses of structs. The weaknesses of structs is in C, we could not add this function inside the struct. We couldn't bring this guy inside the struct. Instead, we had to have these external functions that operated on structs rather than the struct being able to do its own stuff. Okay? Not really a problem. We can still pull things off, but object-oriented languages gave us this new construct called a class, which is a struct that allows these dudes to live inside of it. All right, so when we add a class to this argument, let's just go to another screen here. Let's copy this, paste. Ooh, hello. So we're going to change this to the name class. We're going to grab this code here. we're going to suck it inside of our class. And we actually no longer now need to take in a parameter because this guy already knows about name and age. These guys are local values now to this object. So now we can just say name and age. All right, so that's what object-oriented languages did. They renamed structs to be called classes, and now they allow one new kind of animal to live inside of that structure. That's it. That's the difference between a procedural and an object-oriented language. And along with now this new mindset that when we build our programs, we can build them with the idea of objects. Here's a person and people can do things. Instead of with structs, here's a person and this is the pieces of information that we keep track of for a person. But people can't do anything. That's not consistent with real life. Consistent with real life is we're people, we have a whole bunch of attributes we remember. If you remember attributes from game salad days. But we also have a whole bunch of things that we know how to do. That kind of stuff. Good.
Would this be a simplified version of Blockly?
Oh, well, I wouldn't say simplified. This would probably be a more complex version. This is the syntactic version of Blockly. Although, generally speaking, Blockly forced us into a procedural mindset. If you remember back, you remember last semester when we were using Blockly, by the way, just so I don't forget, I have videos from last semester if you'd like to review those. So shoot me an email or something like that. Or you can probably actually find them on there. But might be boring, might be a lot of content. But if you do get desperate. But most of these guys were not very good at it. So it doesn't really matter. So really, most of us are starting from a decent starting point. And couple of the people will probably be a little bit less bored than they were last semester. But anyways, to get back to what you were saying, if you remember from Blockly, we spent, especially as we started doing more complex things, we were writing a whole lot of little helper functions, right? That's very much a procedural approach to programming. And especially with Blockly, it started getting annoying because you'd have to scroll up or make room for new things and stuff like that, right? Okay, but that's very much a procedural mindset. So one of the reasons I like using that language is it almost forces us now to appreciate being able to encapsulate a lot of that crap into these objects. Well, I mean, we're going to have to write them. So we're going to have a single file in Java, maybe called person.java. And inside of that file, we're going to have a whole bunch of attributes that we're keeping track about people, as well as some functions, for example, that people can do. But once we've written it and it works, just like the telephone, push it to the side, come over here to the rest of our program, and now we just start using person objects. And let all those internal workings that we wrote, tested, make sure they work, be there, but out of sight, out of mind, and now we can just use them. Okay, that's the object-oriented approach to these languages. Can it make sense? All right, so I guess that's kind of the punchline. So I suppose in your minds, maybe think of Blockly as sort of being like a visual version of C, without the syntax type thing. Okay, so this is really our upgrade between C to C++ is the inclusion of classes, which all we did is we drug functions inside of the structs and renamed them to the word method, whatever. All right, now, this is where we were talking about our procedural versus object-oriented. This is where we were talking about kind of how Java's sort of kind of interpreted, sort of kind of compiled. It's mostly compiled here, but because we're running it through a piece of software that maps our low-level language here to our low-level language here, sort of kind of interpreted. But then we started talking about our primitive types. Okay, and these are primitive types, and I've purposely written the primitive types exactly as they appear in Java. So I probably mentioned last time that these are all identical to what's in C, with the exception of how Boolean is spelled. I think in C it's just bool, B-O-O-L, lowercase. C++, it was a capital B. They just started messing with the word a little bit. All meant the same crap. Okay, all meant the same crap. All right, so let's kind of review these different primitive types and why they are the way they are. We probably at least verbally said it near the end of class last time. But forget about char for a second, but we have a whole bunch of different types in Java and in C++ and in C# and in C. Whole bunch of different types that all hold the same kind of crap. Okay? And this is because, as I mentioned a few minutes ago, C is from 1968. Okay, and I probably used the cost of memory example at the end of class last time. Memory used to be ridiculously expensive. Did we actually do any of the math to show the numbers? So what did we come out? Something like $130 per megabyte back then. And this is like in 96. All right, how much worse do you think it was in 68? Probably a lot worse, right? The idea of a megabyte was unheard of in 68. Now, a megabyte is kind of like, maybe today what we think of as being a 10 exabyte hard drive or something like that. That's the thing that comes after terabytes. Okay. Like right now we're kind of sort of impressed with like those 3 terabyte drives, but lately we've almost kind of rolled backwards a little bit. The size is getting smaller, but the speed is getting faster as we're kind of moving into like solid state stuff, right? So you buy a new computer today, you can upgrade from the 1 terabyte hard drive that comes with a laptop to the 512 gigabyte solid state drive. That's better performance. That's today's kind of thing. Fast forward 3 or 4 years, what are we going to do? We're going to start getting within reasonable price range 2, 3 terabyte solid state drives that cost like what our current 2 and 3 terabyte mechanical, quote, slow drives cost. All right, so that's our current little stage on things. But back in the 1960s, little tiny pieces of memory relative to what we view as being memory today was absorbently expensive, just ridiculous, okay? So when C was designed, it was designed with that in mind and said, okay, one of the jobs of a computer programmer is to be a good steward of that memory. We need to use the computer's ability to remember crap as efficiently as possible because the computer can only remember so much crap, okay? Last time, did we talk about kind of like the old vacuum tube stuff? Talk about that at all in here? Okay, now I flip-flop with some of my other classes. But so before we had the transistor, computers used to be the size of a gymnasium, right? We probably talked about this maybe in 150 or 175, UNIVAC, EDVAC, one of those dealies. Maybe they showed you a picture. So basically we represented numbers as a whole bunch of light bulbs, right? So we talk about bits and bytes, zeros and ones. You would have an 8-bit number, for example, and you would turn on some light bulbs and turn off some light bulbs, and those were zeros and ones that represented a number. Well, we can imagine that back then we can only represent so many numbers just due to the physical space that it takes to put a whole bunch of light bulbs. Well, then we got transistors, and transistors represented those light bulbs, but in really, 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 really tiny packages. So now we can fit millions of transistors in much smaller spaces than gymnasiums. All right, so, but the punchline there is memory was very expensive, even in the transistor days, and we had to be good stewards of it as programmers, because we only had so much of it to go around. And if we used up all of our memory storing only a few things, we couldn't write very complex programs because we wouldn't have the memory to continue on with the program. All right, so C gave us a whole bunch of different primitive types, which are types built into the language only capable of holding a value, right? We're going to throw in the quick little definition of primitives. Variable types built into the language that are only capable of holding a value. All right. And Java and C++ and C came with these primitive types. And because of C, we have a whole bunch of different ways of holding the exact same kind of value. So 4 different ways of holding whole numbers, like 3 and 7 and -2, things like that. All right, so I'm going to replace some of these. A byte is a signed 8-bit number. That's what a byte is. We'll talk about these here in a second. A short is a signed 16-bit number. An int is a signed 32-bit number. A long is a signed 64-bit number. All right. First of all, what does it mean for a number to be signed? We have, in computer science, we have two different kinds of values. We have signed values and we have unsigned values. Layman's terms, that's signed values can hold negative signs. So they can hold positive and negative numbers. Unsigned values, all positive. All right. So that means that for these signed values here, even though this guy is 8 bits, we use one of those bits to represent the sign. Is it a positive number or is it a negative number? So that means we actually only have 7 bits to represent the actual value of that number. Make sense? So this guy translates to plus or minus 2 to the 7th power, which translates into negative 128 to positive 127. That's the range of values, range of integer values that fit inside of a byte. All right. Short, plus or minus 2 to the 15th. This is negative 32,768 to positive 32,767. Int, plus or minus 2 to the 31st. Subtracting 1 bit off of it. So this is negative 2 billion to positive 2 billion. And then a long, plus or minus 2 to the 63rd power. This is negative giant number to positive giant number. All right. I think the number is something like 4 quintillion or quadrillion. I think it's quadrillion, 4 quadrillion. Something like that. It's this number, 2 to the 63rd, that number. So looks like 9. 9.2 quadrillion is what it is. Okay, big number. All right, so those are our different types that we have for holding integers, signed integers, positive and negative whole numbers, no decimal places. All right, the reality is today, you will never use a short. Right? I feel fairly confident in saying you will literally never use a short. You will use ints very often. You will occasionally use longs, and you will occasionally use bytes. Modernly, the programmer mindset is different. If you were writing software in 1970, you had to be very specific. If you were counting between the number 1 and the number 10, you're going to find the smallest footprint that you could use to store the numbers 1 to 10. Well, 1 to 10 fits comfortably inside the range of negative 128 to positive 127. No harm, no foul. Okay? We don't do that today. Today, you want to hold a number? Oh, we're going to throw it in an int. We've got plenty of 32-bit chunks of memory to go around, right? So, today your computers come with 4 gigabytes or 8 gigabytes, and we'll review that here in a second. That's a lot of ints, right? A lot of bits go into that. So if you have, let's use 8 gigabytes as an example. So 8 gigabytes is 8,192 megabytes, which is 8,388,000 kilobytes, which is 8 trillion? Yeah, 8.5 trillion bytes, which is that many bits divided by 32. That's the number of ints we can hold in 8 gigabytes of RAM. So that's 2,146,483,648 unique integers that we can store in our programs. So as long as you're not going to write a program that's going to require you to hold too many numbers, that is 2 trillion numbers, which isn't completely absurd, but mostly absurd for what we do today, right? You don't really need to worry about memory too much for most of our applications. All right, so now, and we'll review that bits bytes thing because it's actually pretty important. I know we talked about it last semester, but I'm assuming most of you forgot. So, in any case, we have all sorts of different ways to hold this stuff, but what we do as developers today is we use an int to hold whole numbers, unless it's not big enough, then we use a long. And if that's not big enough, then we start going over to the objects that are built into the language. Java, for example, has an object type called big integer, which holds arbitrary size integers, but the larger the number, the slower it gets. We'll look at some of those, but that's today's punchline. Our default go-to move, regardless of how small the value is int, to hold signed whole numbers. All right. Now we have chars. Chars are unsigned 16-bit numbers. So these do not hold negative values. So that means it's 2 to the 16th power, 0 to that number. So this is 0 to 65,535 is the range of values that fit inside of a char. Okay, now this comes back to this concept of us versus computers. This whole thing of why programming is difficult for us. I mentioned earlier today that human beings were good at problem solving with other human beings. We suck at talking to this alien that is a computer. Right? So we'll call this, we'll just do data representation for now. Computers like numbers. Humans like words. Or pictures. We're good with pictures. It's actually kind of a funny thing. Swift, I haven't found a use for it yet, but Swift has actually included as part of the programming language the ability to use emojis. Going a little far. Have you seen this commercial about you can now text a pizza emoji to Domino's? Have any of you done this yet? I don't know what it's like. I mean, I assume when you do it, do they start this expert system where they start asking, okay, what size, what kind of crust? Is it just start the ball rolling? Because the commercial kind of advertises it, oh, I send them an emoji of a piece of pizza and they send me my favorite pizza. Weird stalkers. So extra credit if somebody can explain to what. Did I spell this wrong? Represent. Oh, yeah, way off. That's way off. Nailed it. All right, so yeah, extra credit if somebody can explain that process on Slack, because that would be very entertaining to see how they've taken the emoji to pizza ordering, because it was just too difficult before. Okay, so in any case, computers are all about numbers. 100% of the time, they hate anything that's non-numeric. Really, they hate everything that's not just zeros and ones, so it's even worse. Human beings, we like things a lot more general than that. Question I typically ask is how many of you know your best friend's phone number? And at least several of you don't, right? Fair enough statement? Okay, because we remember their name. Okay, so we can tell Siri or our Android phone, call Jeff. Okay, or some of us just use the picture, right? We get just a grid of pictures, and I'm going to call the friend that looks like that. Okay, we click it and it makes the phone call, right? That's human beings, right? When I was a kid, I remembered my best friend Jeff's. I knew his phone number, and when my wife and I started dating, I remember her phone number. What's actually funny is she uses the last 4 digits of that number now for some pins for things. She's had to retrain me to remember this number, because as human beings we hate that. So even when we go back to those telephones, we all know how a telephone works, even though we don't use them that often, right? Most of us haven't probably used a physical non-smartphone or non-cell phone telephone a pretty long time, right? Or that would at least be a relatively common occurrence today. Okay, the idea of landlines has kind of gone away and that kind of stuff. But most of us feel fairly confident that we sort of know how phones work. So if I gave you an exam where I put a random phone off Target's shelf in front of you and said, make a phone call, here's the number to dial, you could probably pull it off, right? Okay, well, what was the first new technological advance for telephones? Well, first we had we used to have the rotary thing. Well, before that, you just picked it up and talked to the, you had the thing, you talk to the operator. I want to call Fran down the street, right? Like the black and white TV shows, But then you had the dial thing here where you had to build up the callus. Okay. Oh, seriously, you'd get the phone dial in callus. Any of you ever used one of the rotary phones before? Okay. I bet you those are probably expensive if you go and buy them on eBay now. Probably people want them because it's, I don't know, eclectic or something. So first what we did is we replaced with buttons. So we like buttons. Okay. Then what do? Well, we don't want to push buttons too much. They started adding just a little bit of memory to your telephone. This was back when memory was still pretty expensive. You had the speed dial, right? So you had just individual buttons. I had a button that had Jeff next to it. Click that. And that's when we began forgetting our friends' numbers. Okay. So and then my mom had a little a book that actually had people's phone numbers written in it. Any of you still have like a physical book filled with paper that has people's numbers written in it, or really? That's creepy. You walked right into that one. We do everything electronically now, right? Okay, so we've seen these things evolve, but the punchline is human beings we keep walking this path towards making our life easier. Power tools, things that remember crap for us. One of even in education, this is something that, as professors, we deal with all the time. It's easy for us to say, I look at students today. This is my 17th year teaching. So when I first started teaching, the students were very different. Okay? And it's easy to say, well, students today are dumber than students were back then. The nature of a student has just changed. Your age group relies so heavily on technology that you lack all these skill sets that the people before used to take for granted. So for instance, how many of you would only go to a library as a last resort? Most of us, right? Myself included. Why? Because we have the Google. Right? You go to the magical internet and you click into Google, you say what you're searching for, you trust that it's giving you decent information. But we have these power tools available to us, so we've lost these other skill sets. We've become so reliant on technology and so complacent with other things having to retain knowledge so that we don't have to. We can remember all the video game cheat codes and stuff. That's what sticks in here. Like they still reference that it probably, how many of you played Contra? Nope. How many know what I'm talking about? Anybody know the cheat code for Contra? I still see it referenced on Facebook and stuff like that, and I just assume people knew up, down, left, right, BA, start. Whenever you see that, that's somebody who grew up in the 80s referencing the invincibility code for that video game. So, punchline is that stuck with me. I remember that, but I don't even know what number. Well, actually, I do. I know the first 6 numbers of my, including area code, of my best friend in elementary school's phone number. And after that, it's gone. Completely useless. Okay, so human beings keep evolving down this path of making our life easier, relying more and more on technology to do stuff for us. I think I told you last class I'm giving up walking next week, right? I got my hoverboard coming in. Who needs to walk when you can just zip around at 10 miles an hour? I can't sprint at 10 miles an hour. I can't sprint at 2 miles an hour. I can't sprint. Okay, so who needs to do that anymore? Now I don't need to worry about legs, right? Because I got the replacement. So I'll give somebody else my legs. Right? I need to get I always wanted to kind of do like the Octoman, almost like the spider Terminator legs. Wouldn't that be kind of cool? That would be freaky to go to. The creepy things you hear in class. All right. So, anyways. Computers love numbers. That hasn't changed. Human beings, we do everything we can to not have to remember as much stuff as we can. That immediately creates an incompatibility for us. Okay? And we have to bridge that somehow. And we talked about programming languages last time. Basically, we can't rely on human beings to change too much. All right, we already have this perception that computers are difficult and stuff like that. But the reality is human beings have become very used to the conveniences, that we have. If we were back in the 1800s, the fact that it's warm in this room wouldn't be a big deal. Today, we're like, well, who the hell turned off the air conditioning? I'm going to pay my $25,000 tuition. This is ridiculous, right? How many of you were thinking that? All right, so we have to have technology that lives in the middle that makes our life easier and more compatible with how computers work. And this is where data representation comes in. So under the hood, all of our stuff inside the computer is actually represented as numbers. 8-bit numbers, 16-bit, 32, 64. Okay, well, what's a bit? What's a byte? All this stuff. Let's talk about that relatively briefly. Let's go this route. Okay, so we have a bit. A bit is a 0 or a 1. Okay, we have a kilobit. Okay, kilobit is 1,024 bits. We have a megabit, which is 1,024 kilobits. We have a gigabit, which is 1,024 megabits. And we have a terabit, even though nobody actually uses that phrase right now. 1,024 gigabits. All right. On the other side of the equation, this is where we have a kind of consumer fraud going on. We have the idea of a byte. A byte is actually 8 bits. A kilobyte, big B, is 1,024 bytes. A megabyte, big B, is 1,024 kilobytes, big B. A gigabyte, big B, is 1,024 megabytes, big B. A terabyte, which we do use, is 1,024 gigabytes. All right. Now, where we have the consumer confusion, where we see this most often is with internet connection speeds, right? So, how many of you have internet at home, DSL or cable? Okay, so DSL, you probably have, 6 or 8 or 10 or 12 megabit per second. Cable, you might have 20 or 30 or 50. Some places have 100. Couple of bigger cities now, Google has gone into as gigabit internet. But most of us immediately translate the megabit into megabyte, right? When we hear 30 megabit per second internet, we say, oh, we can download 30 megabytes per second. Doesn't work that way. It's megabit, small b. So for instance, at my house, I have pretty fast internet. I have a 100 megabit per second internet speed. Okay, well, 100 megabit per second is 100 divided by 8, 12.5 megabytes per second internet. Okay, so understand that that mapping is, from a consumer's perspective, bigger numbers are better. So that's why the internet providers say it's 100 megabit instead of 12.5 megabytes. Because most of us, if we were comparing 50 megabit compared to 12.5 megabyte, we're not going to understand the difference between these two. So we're going to say that, oh, this guy's better. When actually this guy is half the speed of this guy. Make sense? Kind of an interesting consumer awareness type thing. Okay, so when we deal with computers, we're always dealing with, at the core level, this idea of a bit. Bits are singles, zeros, and ones, and we use collections of bits to represent values, represent numbers. All right? Now, as an example, as a reminder, just so we see how this stuff works again, I mentioned that an 8-bit number can hold values in the range of negative, well, a signed 8-bit number can hold values in the range of negative 128 to positive 127. And one of those bits is used for the sign. So really, it's 7 bits represent the number. Okay, so if I have the number, that's a 7-bit number. That's decimal 0. This is the ones place, the twos place, 4s, 8s, 16s, 32s, 64s. Similarly, that's the decimal number 1. That's the decimal number 2. We have a 0 in the ones place, a 1 in the twos place, and a 0 in all the other places. Three, 4, 5, so on and so forth. So our biggest number would be this. Okay, so this is a 1 in the ones place, a 1 in the twos place, a 1 in the 4s, 8s, 16s, 32s, 64s. So this is 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, which should be 127. There's our 127. Okay, so that's where those values come from. Computers are representing that number like this. Okay, the negative 128 thing comes from that. It's called a register overflow thing that actually rolls it over and gets you to the extra 1 because of the sign. So it's a thing. All right. So in any case, that's our bits, bytes type stuff. It's called bits stuff. All right, so important to understand for us, at some point we're going to write a program that will convert this stuff like we did last year, but we'll do it in Java. But for our perspective related to what we're talking about right now, it's important to understand these things from the perspective of what these different things are for, how these different variables are built for holding different size values, and how that actually works under the hood. So we have this guy right here, a char, which is actually an unsigned 16-bit number. So we no longer need to use the zeros or ones. So I have 16 zeros and ones. So 16 ones will get me 65,535 if I do all the math. Ones, twos, fours, and 4096, get a little crazy. All right, but it's unsigned because the char primitive type, which from a human perspective is used for holding characters like A and B and the character one. In Java, characters are represented with single quotes around them. All right, so a character literal is a single quote followed by a single character followed by a single quote. And that character can be a number. That's the character one, not the integer one. Make sense? Because it has the single quotes around it. Now, the reason why we have 65,536 unique numbers for characters is Java uses a character set called Unicode. Unicode has a lot of the world languages in it and things like that. And because, as I've advertised, computers like numbers, what Java does is they say, okay, well, we're going to represent all of our characters as a gigantic indexed list of numbers matched up, which map to an individual character. Make sense? Okay, so again, computers can just remember a whole bunch of numbers and then have in their memory the mapping from that number to this character. Human beings, we don't want to have to remember the Unicode value of a capital B. We'd rather just remember the letter B. Already got that in there. We're not going to work any harder than we have to. Okay, there's not a whole lot of value. There's probably people who have memorized the ASCII character set, which is only 256 unique characters. That would be creepy, but within the realm of reason. If anybody comes up and has memorized the Unicode character set, probably punch them and run. It would be a reasonable approach, I would think. Although there's some of those folks that have memorized a pi up to thousands and thousands of decimal places. So I mean, I guess technically I'm saying punch them too, but we don't really condone that here. So do it anyways. All right, so that's why we have the unsigned character, is to represent a whole bunch of different languages. So the char primitive type in Java holds characters potentially from all sorts of different languages. Bad news for us is even though the Unicode character set is capable of holding characters from all these different languages, the reality is that most of our terminals, when we view the output of our programs on American-based operating systems, they're not capable of showing the Unicode values from foreign character sets. So you're pretty much stuck with the first 256 American characters, which is kind of sad because actually we only have so many characters in our alphabet, upper and lower case. Then we have the numbers. We've got some punctuation and stuff like that. So the rest of it, what do we fill up? We fill up with like little smiley faces and we have like some card faces for like playing cards. Yeah, it's really kind of sad when you look at the history of computing from the perspective of Americans. Like, well, these are the things we deem to be important. If you've ever opened up like a binary file, like tried to open up a .exe file on Windows inside of Notepad, sometimes you'll see all the weird symbols. You'll see the smiley face, and then sometimes you get the black smiley face. Like that's not racist, right? Okay, so funny computer science history stuff. All right, floats. Floats are for decimal point numbers. 3.14, stuff like that. So a float, decimal point numbers, we're going to say kind of like an int. A double is decimal point numbers, kind of like a long. All right, so technically I think floats are 32 bits followed by a decimal point followed by 16 bits. And double is 64 bits followed by decimal point followed by 32 bits. That's the footprint of a double. Okay. Now the reality is, and it's kind of a little bit backwards, I guess. I've told you that on the integer side of things, our default go-to move is pretty much int. We only use a long if an int isn't big enough. Okay. But on the floating point side of things, our default go-to move is double, not float. So those are if you were going to look at this and decide what are the things you're going to use very often in Java, int, char, double. Probably your three go-tos. You'll use the idea of Booleans often, but you probably won't store Booleans and Boolean variables all that often. We do Boolean expressions very often. Okay? So, going to store a floating point number, put it in a double. Going to store a whole number, put it in an int. Bytes, nobody ever uses bytes for just storing small numbers. Bytes are still used relatively commonly for like streaming type video applications because we typically stream stuff in 1 byte chunks, okay, or at least collections of bytes. So we read them into a byte array, a collection of bytes, and then work with them as individual bytes, not because of the size of the value being anything important, but more just that's how the values are organized. Okay, so that's why bytes are still used. Like I said, you'll never use a short. They might as well remove it from the language. And actually, you'll never use a float unless you're using somebody else's library that they put together that happens to use floats from like an old C library or something. So generally, as modern programmers, we'll never use float as a primitive type. Okay, Booleans. These are true, falses. From a human perspective, under the hood, these guys are actually represented as zeros and ones. So we use a single bit to represent our Booleans, although the smallest footprint value that we can store in our modern computers are bytes. So we actually use 8 bits to represent. So we either have 8 zeros or we have 7 zeros followed by a 1. That's what represents our Boolean false and our Boolean true. Make sense? Okay, so Boolean true false is kind of like on versus off, that kind of stuff, and we solve all of our modern programs from the computer's perspective in terms of a whole bunch of little questions. If you've seen it's either The Price is Right or the other one where they have the Plinko. Seen that one where they drop the coin in and just clicks down until it falls into the big money or the no money buckets, right? Okay, so that's kind of like how digital logic works. We have our input, or usually multiple inputs, and they drop through a whole bunch of decision-making gates. They're called, hardware. When we talk about building hardware, for those of you who are going to take the organization class probably next semester, 325. Is that right? Is that offered next semester? I teach it, but I'm the last to know. But in any case, we basically write programs in hardware. That's what the class is. We build gadgets, okay? And we do that with a whole bunch of little what are called, logic gates. And what's a logic gate? It's a Boolean expression. So here's two inputs. We're going to apply the AND logic to it, and we're going to get a single output from that, either on or off. We have the OR gate. There's two inputs. We're going to apply the Boolean OR logic to it, and we're going to get one output, either on or off, so on and so forth. So when we think about our pieces of hardware, whether it's our computers or the telephone example we had there, internally, what's actually happening? We have our inputs coming through, and they're going through that Plinko board. Is that what it's called? Plinko? I got you're a fan? Which show is it?
Wheel of Fortune.
It's not Wheel of Fortune. I know it's not that one.
Price is Right.
Is the price? We have Price is Right, and what's the other one? Let's Make a Deal. Let's Make a Deal is like the competitor, right? But it's Price is Right is the Plinko one. Okay. Yeah. So in any case, your inputs come in, and they kind of dance through the whole thing until you have your output. And that's just stuff going through a whole bunch of little digital logic gates. Inputs, output. Output's always a 0 or 1. On or off. Some electricity or no electricity. That kind of stuff. Okay? Everything's built in terms of that stuff. But again, human beings, we kind of like the words true and false as opposed to using a whole bunch of zeros and ones. A little bit easier for us to digest. Another programming language that would actually fit here is a language called Objective-C, which is kind of Apple's language until more recently when they went to Swift. Instead of true and false in Objective-C, they use yes and no. Kind of a funny macro they use for it. So, okay. So there's our bit stuff, there's our conversion stuff, blah, blah, blah. We understand that humans like non-numbers and computers like numbers, and somehow we need to close that gap, right? And that's why we have all these different primitive types for doing different things. At the end of the day, we want to understand this crap, but whole numbers, right there. Floating point numbers, right there. And then chars we use to store chars. Those are the three biggies that we really need to care about. All right, so now here comes the monkey see, monkey do part of the class. So what you'll be doing for your homework assignment is what I'm going to be doing next. Okay, in every single class, every single programming language rather, you always do your proverbial hello world program. That's your first program. Make hello world show up on the screen. All right, so in here, we're going to actually be using a tool called Eclipse. But I'm going to show you Hello World without using Eclipse. Because again, we want to appreciate what these power tools are doing for us. So I'm actually going to open up my terminal here. So think of this like as old style DOS. Brad's iPhone. It's very funny how Apple's Bonjour networking thing works. So apparently somebody must be sharing something in the network, and my terminal thinks I'm on Brad's iPhone. All right, so in any case, I'm going to go ahead and do, this is a text editor, VI, don't worry about that. You won't have to do this. So I'm going to create a Java program. We're going to call this guy hello.java. Our very first Java program. All right, it's going to look like this. Now, every single Java program you ever write will start off with the word public, treat what I'm saying right now as true. There's a couple little caveats there. But let's just say public, followed by the word class, followed by the name of the .java file. So in this case, we have a file called hello.java, so we're going to name this hello. So we have public class hello, and then I have my opening and closing curly braces there. All right, so every Java program, as far as you're concerned right now, will always start this way, where this word right here matches identically, case sensitive and all, the name of the file. Good news is the tool we're going to use in here does all that for you. Does that part of it for you, okay? But just for your own knowledge, this is how they all start. Then we have this idea that all programs begin and end with main. We have this thing called a main method, and this goes way back to the C programming language. I'll show that to you here in a second, but we have public static void main string array args All right, so here's our main method. Don't worry about some of this crap out front. Just know that main must always look this way for right now. We'll learn about what all this crap is later. All right, this part here is the parameters that go into that function. This is for command line arguments. Again, we'll also talk about that later. For right now, this is what main looks like. This is what main does right now. In Java, this is how we display something to the screen, using system.out.println. And this puts a carriage return after it. There's a system.out.print that doesn't put a carriage return after it. Okay? So this is the entirety of our de facto hello world program. Now I'm going to go ahead and save this file. And what I'm going to show you here is what's actually happening behind the hood, or under the hood in Eclipse, the tool we're going to be using in here. So I'm going to save this file. This is just a normal text editor. The file's saved now. All right. I need to now compile it. If you remember back from our lecture here, we have our Java code, which we just created. Now we need to compile it into Java bytecode. And we're going to do that using the Java compiler. If you have a Mac, the Java compiler is built in. If you have a PC, you'd have to download it, but it actually comes with Eclipse. Does it come with Eclipse still? It might come with Eclipse. Okay, well, I guess you'll find out when you download it. So if not, I'll show you where to go here in a second. But I'm going to go ahead and compile this. Macs do. Is that what you were just saying? You don't know if Macs come with it?
No, well, if you try to do something in Java, it'll prompt you to download Java.
Yeah, that's the Java plugin for the browsers and stuff. I think it's still there for at the terminal, but you might be right. I know exactly what you're talking about. I've got the warning too whenever I install a fresh OS. But I think this has always worked. Let's see if it's going to still work. Yeah, it's there, but it's possible I'd already installed it. Unimportant, you won't be doing this stuff, but punchline is I need to compile the code. So I'm going to type in JAVAC. This stands for the Java Compiler. It's a program that is installed on my computer because either Apple installed it by itself with the operating system or I've downloaded it from Oracle, used to be called Sun Microsystems. And I'm going to compile the program hello.java. So that's my Java source code file. I'm sending it to the Java compiler. Press enter. If I didn't have any syntax errors, it'll just go right back to the screen there. But I'm going to do notice we have a brand new file that got created here. Hello.class. That is my Java bytecode. Okay? So first three steps have now been completed, but I had to manually go through those. Now we get to the Java virtual machine to actually run this guy. So I say Java hello, and there's my hello world. Okay? Now, for us in here, what we're going to be doing is we're going to be using a tool called Eclipse. I'll go ahead and open this. Let me actually just real quick here. Just going to steal this code. And I'll show you where you can get Eclipse in a second, but I give you a link to it in the, I'm actually using a little bit older version of Eclipse here than you'll be grabbing, but it's all the same. So I'm going to go to File, New Java Project. I'm going to call this project Hello. Default location's fine. All this other stuff should be default. Don't have to do anything special. So just hit Finish. All right, so now here is my project. So that's going to give me a little directory structure thing over here. And inside here, I'm going to have a folder called Source. All right, I'm going to right-click on Source, and we're going to create a new class. And the name of my class is going to be Hello. This will create the hello.java file for you. You can name it whatever you want. It could be elephant.java for all I care. But remember, the name of the class must match the name of the file. Eclipse does this for you. All right, now, a couple of interesting things here. Notice that with Eclipse, they're asking which method stubs would you like us to create. You could actually have it go ahead and put main in there for you if you want. You can just click that box and they'll put main in there. I would encourage you not to do that initially. You want as much practice typing in syntax as you can possibly get because you want to make all your mistakes now. So as you're working on homework assignments and stuff like that, I understand you guys are going to go and you're going to Google stuff and look for examples. That's fine. I also encourage you to work in groups and try to learn stuff. But whenever you have code that you want to try, don't copy and paste it. Type it as much as you can because that will help you a lot in reducing the number of mistakes you make. Because you'll make all the mistakes that you are going to make by forgetting a semicolon here, forgetting an opening curly brace, and then by going back and having to fix those mistakes, you're going to be reinforcing yourself to not make them again. But if you're always copying and pasting code, you're not getting that practice. All right, so the name of the file will be hello, and that's going to go ahead and create this public class hello for me. I'm going to just kick that down a line real quick. Actually, let me just do this. So there's my file. Now, all that stuff I did before, the JavaC, blah, 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 in here, you just hit the play button. There's Hello World. Okay? So for your homework assignment, you have to do that and give me a screenshot of this. Code up here, running program down here. All right? Now let me show you where I got this stuff in our final minute. So Eclipse, and I give you a link to this in the homework. So I'm going to go to eclipse.org. It's going to take you here. Eclipse is actually something that's created by IBM. It's like the de facto Java integrated development environment. So the Java tool that we use for writing Java programs. Text editor on steroids. So you go there, you click on download. It'll figure out what kind of machine you're on. You can check this if it changes, but it's detected I'm on a Mac. If you have Windows or Linux, choose that. You want the Eclipse IDE for Java developers, not the one that says Eclipse IDE for Java EE developers. You want this guy right here. Go ahead and download it, install it on your computer. If for some reason you don't have Java on your machine, if it complains about that once you open it, then what you want to do is you want to go to java.sun.com, which should map to Oracle here in a second. And then up here it says new downloads. Do Java SE8 update 60, it looks like. Go ahead and click on that. Go ahead.
You are running Java 6 right now in your Eclipse. So you want us to use Java 8 because there's a little bit of syntax.
It should at least work with that. There shouldn't be any old syntax issues. So Eclipse should work with anything X or newer. So I think it's either Java 6 or Java 7. I think when I do Android Studio, I have to do at least Java 7. So it shouldn't matter, any of the newer ones, especially for the stuff we do in here. There might be, I mean, usually it's a superset. They deprecate some old stuff, but there shouldn't be any major syntax errors that will impact us in here, I guess is what I'd say.
I mean, yeah, when I was learning Java in the past, we've had issues, even just between 6 and 7, just really minor issues.
Okay.
In the way that certain things had.
Do you have an example of anything or not necessarily?
I don't remember, but
All right.
it was pretty basic. Though.
Okay. Well, we'll figure it out. I haven't bumped into stuff, but in any case, only if Eclipse makes you do that. A lot of times Eclipse has its own runtime environment that comes with it, but there might have been some sort of changes there. But in any case, for your homework that's due on Tuesday, do what I just did. create a screenshot of that, submit the screenshot. Okay. I also posted on Slack something about the self-assessment thing. I want you to turn that in with every homework assignment. So including this one. So if you didn't check that on Slack, go and read about that. And then, that's it. So I'll see everybody on Tuesday.